In this work, I'll present my work on smart wristband-based stress detection framework for older adults with cortisol as stress biomarker. This work is recently published in the IEEE Transaction on consumer electronics. Older adults aged 60 and above are most susceptible to age-related illness. Most of these illnesses, such as hypertension, diabetes, etc., are some effects of long-term stress, and these lead to irreparable damages that happens over time. So in this work, our objective is to design a wristband-based wearable solution for detecting physiological stress. Our method uses salivary cortisol, which is a clinically established biomarker for stress. These are some of the related works on stress detection for older adults. Our work explores a novel method to detect stress using wristband sensors, as they're easy to adapt and use, and using cortisol as the ground truth for stress together. Our research is also based on a large participant pool of 40 participants, and this work is the result of experimental study that continued for over a year. This is the overall block level diagram of the proposed work. So the smart wristband that we are using in our work is embedded with EDA, PPG, and skin temperature sensors. This sensor outputs EDA, the PPG sensor outputs the BEP and IBI, and ST sensor outputs the skin temperature sensors. And these signals can be captured in recording and streaming mode, and then later can be synced to a cloud platform for processing and model training. For training and testing the model, first of all, the signal needs to be pre-processed, and then the features needs to be extracted. After the features are extracted, the feature samples needs to be annotated with stress labels, which are obtained from the cortisol concentration. The cortisol concentration is obtained by immunoassay processing of the saliva samples that are captured during the TSST protocol by placing a swab under the tongue for about 2 minutes. And finally, the feature set will be used for training and testing a random forest classifier. For this study, we used data of 40 participants, 40 older adults in the age range 60 to 80. The participants were screened for some existing conditions prior to enrollment. Physiological signals and the cortisol samples were collected during the TSST protocol. The objective of the TSST protocol was to induce stress through speech and mental tasks. The TSST protocol is shown in this figure. For modeling, EDA and BVP signals are first normalized and filtered. ST signal is only normalized and filtered for missing values. No pre-processing is done on the IBI signal. Total of 47 features are extracted from these 4 signals. EDA and BVP contributed 18 and 17 features respectively, and IBI and ST contributed 6 features each. The features extracted were simple statistical measures of the peak characteristic of EDA and BVP signals, and simple statistical features from IBI and ST signal. The salivary cortisol were collected at time points T1, T2, T3, T4, and T5, which are 20 minutes apart, shown in the figure. The table shows the statistics of the cortisol concentration at different time points. To get the stress levels from cortisol concentration, the samples at T1 and T2 are averaged, and their values are subtracted from T3, T4, and T5 for each participant. Then the samples at T3, T4, T5 are from all such subjects are integrated and standardized. And if the z-score of a particular sample is less than the population mean, the sample is classified as not stress, and if it is greater than the population mean, then the sample is classified as stressed. This is the statistic of the stress and not stress class. The p-value shows a significant difference between these two classes. The feature set is then split in the ratio of 75 to 25 as training and test set. The training set is then used to select significantly correlated features from each signal stream. Finally, a total of 27 features were found to be significantly correlated with the stress levels. This is the taxonomical representation of the selected features. This table shows the performance of the stress detection model on the test data for different signal combinations. We can see that the accuracy increases as features from different signals are fused. From the table, we can see that using EDA alone gives F1 score of stress class as 0.88. However, the F1 score for not stress class is very low at 0.79. This indicates that the model is good at predicting stress classes using EDA signal alone, but also gives a lots of false positive. So if different signal combinations are used, then this problem is mitigated, as when all the 4 signal streams are used, the F1 score of not stress class increases to 0.90. Similarly, the ROC curve figure of the 4 combinations of the 4 different signal streams also shows the effectivity of the signal fusion technique. This is another visualization of the effectiveness of sensor fusion. The number of mass classification reduced from 54 to 42 when BVP is used along with EDA, and this is further reduced to 22 when all the 4 signal streams were used together. In conclusion, a variable solution for detecting physiological stress using cortisol as the ground truth, which is an established clinical biomarker for stress, is proposed. Out of the 47 features extracted from EDA, BVP, IB, and ST, 27 features were selected to train a random forest classifier. Results showed that this work is suitable for continuous and unobtrusive monitoring of stress in a smart home environment. In the future, this work could be extended to include stress management strategies by launching personalized intervention. Thank you.